I'm creating a series of videos on normal form equations of straight lines. This is the first one. There are many types of linear equation forms, such as slope-intercept form, point-slope form, standard form, and so on. Among these, the normal form is not that popular, but it has very rich geometry properties and can be used to connect geometry and algebra. Normal form is similar to standard form, with an additional restriction that the sum of the squares of leading coefficients equals 1. In some books and videos, it is also required that the constant c is not negative, but I don't apply such requirement in my videos just for convenience. The constant c in my video can be positive, 0, or negative. An example, consider equation 3x plus 4y equals 12. It is not a normal form because 3 squared plus 4 squared equals 25, not 1. However, if we divide by 5 from both sides of the equation, it becomes a normal form because 3 over 5 squared plus 4 5 squared equals 1. So the process to converting a standard form into a normal form is called normalization of the equation. In general, if we have a standard form equation, capital AX plus BY equals C, we can normalize it by divided by the square root of A squared plus B squared. Let's look at this example in details. Using this normal equation, we can create a linear function f of x and y, defined to be the left-hand side minus the right-hand side of the equation. We will plug in different coordinates x, y, and see what would happen. First, if the points are on the line, then the function's value would be 0. Of course, they satisfy the equation. Secondly, if the points are on one side of the equation, they can be either all positive or all negative. For example, in this case, on this side of the line, all function values are negative. For example, if we plug in the origin coordinate 0, 0, the function's value would be negative 12 divided by 5, which is negative. If the points are on the other side of the line, the function's value would be positive. So far, all the observations apply to any kinds of linear equations, no matter what form it is. Now, let's look at something special for normal form only. For any point in the plane, the distance from the point to the line is the one from the point to its perpendicular foot on the line. In order to calculate the distance, what we need here is that we plug in the coordinate in the equation and calculate the difference of the left-hand side and the right-hand side, take absolute value. That would be the distance. Is it enough? Let's look at an example. The origin 0, 0 to the line, what would be the distance? You simply plug in 0, 0 into the function f of 0, 0. It is the absolute value of negative 12 divided by 5, so the distance is 12 over 5. Let's prove the result. we begin with a lemma. The distance from the origin 0, 0 to the line ax plus by equals c is the absolute value of the constant c if the equation is a normal form equation. We assume a and b are not 0. If one of them is 0, then the equation would be the line that's parallel to either x-axis or y-axis. Then the result would be very easy to verify. Under this assumption, the x-intercept would be c over a, assuming y equals 0, solve for x. Similarly, y-intercept would be c over b, assume x equals 0, solve for y. In this case, we establish a right triangle OAB, with OA equals absolute value of the x-intercept, OB is the absolute value of y-intercept. We use absolute value because we don't know A, B, C are positive or negative. By Pythagorean theorem, the hypotenuse AB would be the square root of the square of x-intercept plus the square of y-intercept. Simplified, the square root of c squared times a squared plus b squared divided by a squared b squared. However, we know the equation is a normal equation, meaning a squared plus b squared equals 1. This can be further simplified. We end up with AB equals absolute value of C over AB. Now, let's see. We already have the length of the triangle in terms of A, B, and C. This is a right triangle. We have an altitude from O to the side AB. We call it OD. So OD is the target distance we are looking for. There are two ways to calculate the area of the triangle OAB. First, it can be 1/2 of OA times OB, and the second, it can be 1/2 of AB times the altitude OD. We already know the length OA, OB, and AB, plug them in, and solve for OD. We have OD equals absolute value of C. So we prove the lemma. Now, let's look at the general theorem. The distance from an arbitrary point P with coordinate x0, y0 to the line ax plus by equals c is the absolute value of ax0 plus by0 minus c if the equation is a normal form. So still the same thing. We plug in the coordinates into the equation, and the left-hand side minus right-hand side take absolute value. That would be the distance. Let's prove it. We use a translation from the original coordinate system to a new coordinate system by a parallel transform. X equals x prime plus x0, y equals y prime plus y0. By this transform, we have a new coordinate system. We put the point P as the origin. In the new coordinate system, so the equation of the line ax plus by equals c becomes ax is replaced by x prime plus x0, and y is replaced by y prime plus y0. We simplify it, ax prime plus by prime equals a constant. This time, the constant is c minus ax0 plus by0 inferences. This is also a standard form in the new rectangular system. I'm sorry, this is the normal form. So to calculate the distance from origin to this line, we simply using the lemma we just proved. In other words, the distance we are looking for is the absolute value of the constant term, which is ax0 plus by0 minus c, then take absolute value. The result can be further generalized to calculate the distance from an arbitrary point to a line of a standard equation, not necessarily normal form. The distance from point P with coordinate x0, y0 to line ax plus by equals c can be calculated as you plug in the coordinate into the equation, calculate the absolute value, and then get it normalized by divided by the square root of a squared plus b squared. I will continue the journey of normal linear equations, so stay tuned.